Good evening, everyone. In the last class or class before that, we did one problem, which is that if I have this word Bharat, and how many arrangements of this does not have any columns with the fixed points. That is, for instance, B should not be below B and all those. That's what we looked at. So we used more than one method, but one of the methods, we temporarily distinguish the A's by A1 and A2. And if I just look at all these things, I have 1, 2, 3, 4, 5, 6 letters are there. So the total is factorial 6. Okay, the total is factorial 6. And I need to eliminate those cases in which A1 goes to A2 or A1 goes to A1 itself. So A1 cannot go to A1 or A2. And then A2 cannot go to again A1 or A2. So that's what we have to distinguish. So suppose let us look at this. Let's count how many are there. So if I have this BH, let us consider this A or T. So I have these 5 of them, and then these 5. So totally, since all these things are distinct, so how many ways are there? So that the arrangement says that no letter goes below the whole thing is basically arrangement. That is D6. This B will not go to B, H will not go to H. So that's the total number of arrangements, out of which I have to eliminate this case and this case. Correct? Let's look at how many of them will have A1 will not go to A2. Okay, so that means here I have A1 and I have this A2 also is like this. So if A1 does not go to A2 means what? So A2 is what? So A1 below A1 there is no A2 means A2 is somewhere else. Correct? A2 is somewhere else. That means what I have here is I have something else. That A1 is something else. That is A1 is going to one of those 4 letters. So one of those 4 letters. Let us say whatever it is R. Okay. And the remaining letters are B, H, T and A2. So that is BHT, A1 and so the remaining letters are BH, A1 and let us say T. And of course, A2 will be there. Correct? R is not there at all. So these 5 is what I have to arrange like this. So these 5 I have to arrange. So let me 1 minute. I think I'm goofing off. 1 second. 1 second. We have to watch this carefully. How to explain that? Let me 1 second. Let me check that. This one or what? Yes. Okay. Now. Yes. It's a mathematics. Now let's look at this, for instance. So here I have. So we look at all the arrangements BHA1 RA2 RA2T with no fixed arrangements is this D6. Correct? Now of these arrangements we need to subtract the ones which map A1 to A2. So if A1 is going to A2, what are the remaining letters are there? The remaining letters are BHRAT. This BHRAT, there are no 2 A's at all. There's only 1 A. So I don't have to call it A2 at all. I call it exactly A2 itself, or A itself. So these 5 have to be arranged in such a way that there are no repeated letters in the columns, which means that I have to arrange this BHRAT such that there are no fixed points, and that is definitely D5. That's the D arrangement. Similarly, when A2 is going to A1, A2 is going to A1, again they have 5 letters, and again that will be, look at BHA1RT, again that also is D5. Okay. Now in this, when I say this, when we have this A1 maps to A2, let's see what are we actually doing. So we are actually doing like this. Let me stop this guy and share this. Okay. Now, when I have this BH, A1 or A2T, so my A1 is going to A2. So this arrangement is not, meaning I'm counting how many arrangements will be there, so that A1 is going to A2. So what I'm looking at is BH RA2T will be, or how will that be? That will be this A2 will not go to, say this A2 is only one A is there. So I can just call it as A itself. So this A will not go to A itself if I just consider it as D5, correct? That means I have this will be A, this will be, let us say B, this will be T, and this will be, let us say H, and this will be R. So in none of those D5 arrangements, A2 will be mapped to itself. That means this does not count A1 going to A2 and A2 going to A1. This doesn't count this guy. So it counts only this A1 going to A2, and then A2 is not going to that A1. So that means I have only this is counted. Similarly, when I just release this A2 to A1, when A2 is moving to A1, the remaining are BH and what is the BH and A2 is already moved to A1. So BH, A2 and R and T. Again, this also will be D5. This also will not count any of those. A1 goes to A2 and A2 goes to A1. So when I subtracting two D5s, I am not eliminating both those cases. I'm eliminating only one case, A1 going to A2 and A2 going to A1. And after that, what happens? Now I have to consider and eliminate those in which A1 goes to A2 and A2 goes to A1. So let us see what that means. So I have my A1 here, R here, A2 here, T here. So A1 is going to A2 and A2 is going to A1. The remaining are BH, R and T, and they should not be mapped to themselves. Therefore, that will be D4. So this D4 is the one which counts A1 going to A2 and A2 going to A1, which was not included in any of these two cases. So I have to subtract that as well. So I have D6 minus D5 minus D5 minus D4. So note that these two intersections, neither of them count this case counted by D4. That is A1 going to A2 and A2 goes to A1. That's why we need to subtract it again. So that is the no, this R is not, see, A1 going to A2 and A2 going to A1. That's what I am not looking at in both of the first two cases. So this is not, see, we are counting one by one. A1 going to A2, we are counting first. The remaining the remaining 5, we are arranging using deranggements. And similarly, A2 is mapped to A1 and the remaining 5 are arranged by deranggements. And this does not count A1 going to A2 and A2 going to A1. So that we are subtracting in D4. So that's why we need to do this. Okay. So hope Arnika, your doubt is clear. And if it is not, let me know. Are you convinced? Not yet. Okay. Good. Okay. Now let's go back and continue from where we were in the last class. Let me clear this.
Sir?
Yeah.
Sir, what is the answer, sir?
What is?
The answer.
What the answer is 68. Because we'll get D6 minus D5 minus D5 minus D4. And this will become 160. Yeah, this will become 160. It will be, sorry, it's 84. So it will become 168. And then each of them will be counted twice. So it will be 84. That we saw last class, isn't it?
Okay, sir.
You can look at the notes or also the video and then see how we have it. I also gave some other proof as well, a couple of more proofs as well. Okay. So last class we were here, that is the binomial theorem which we used. In fact, we used this x1 plus x2 plus etc. of the xk equal to n, the number of solutions for this equation in non-negative integers. So this was an extension of stars and bars in non-negative integers. We saw this as n plus k minus 1c, k minus 1, or I can write it as n plus k minus 1c n. And we use this one to expand this 1 minus t whole power minus k, because my 1 by 1 minus t, I can write it as 1 plus t square and so on, using a geometric progression. So if I just want the power k, I will have this power k. This power k will be a sum of this 1 plus some a1 into t plus a2 into t square. All of them are coefficients. When will this, suppose I have the coefficient an into t power n. When will the coefficient t power n will come? When I have k factors here, 1 plus t square, etc. And again 1 plus t plus extra t like this. And I have k factors here. So I could have chosen one x1, t power x1 from here, t power x2 from here, and similarly t power xk from here. So if I just multiply that, I should get t power n. That would mean my x1 plus x2 plus xn must be equal to n. So that's the number of solutions of this. And note that each xi, this x1 can be any one of these powers. This is t power 0. So 0, 1 to any one of those powers. And similarly, this also could be 0. So all these xi's are non-negative. So this is the same as t power n term comes only whenever I multiply all these things and then get the x1 plus x2 is n. And that we already know the number of solutions is n plus k minus cn. So I have this expansion. So if I want this k is minus 2, let us say, so k is equal to 2 means, so I will get, what will I get? This n plus 2 minus 1, c 2 minus 1, which is same as n plus 1, c 1. So the coefficient of t power n is n plus 1. So coefficient of t is 2, coefficient of t square is 3, coefficient of t power n is n plus 1. Similarly, if I have 3, what will I get? It is n plus 3 minus 1, say 3 minus 1, which is same as n plus 2 c2. So coefficient of t power 1 is 3c2. And then coefficient of t square will be 4c2 and so on. So it will become 1 plus 3t plus 6t square plus 5c2 is 10t cubed and so on. So that will be the expansion of 1 minus t equal power minus 3. Okay, so this way we can expand several of them. Okay, that's what we discussed. And we discussed one problem, which was also, we know that the number of 4-digit numbers d1 plus d2 plus d3 plus d4 equal to 26. So how many 4-digit numbers are there with whose sum of digits is 26? So we had here it was d1 must be more than or equal to 1, less than or equal to 9. And all the d8s must be more than or equal to 0 and less than or equal to 9. So we have these conditions satisfied, and then we just translated this problem into something else, and then we counted the coefficient appropriate. Okay, right? Let's look at this problem. So how many solutions are there to the equation xi is a non-negative integer less than or equal to 15? So what I have here, 0 is not equal to xi is not equal to 15. Okay, so I want the number of solutions to this one. So what I need is that I can write it as 1 plus t plus etc. up to t power 15 into 1 plus t etc. up to t power 15, and again 1 plus t etc. up to t power 15 into 1 plus t etc. up to t power 15. So when I expand the whole thing, what will I get? I will get all the powers of t. And so if I take this t power x1 and t power x2, t power x3 and t power x4, so this will be equal to t power 40, when my x1 plus x2 plus x3 plus x4 is 40. And also all the x's will be less than or equal to 50. So this is the number of solutions to this equation satisfying this condition is basically the coefficient of t power 40 in this expansion. What is that expansion? 1 plus t extra up to t power 15 whole power 4. So this we are going to write it in a slightly different fashion. So this I will write it as 1 minus t power 16 by 1 minus t. So this formula most of you would know, that is 1 plus t plus t power 15 will be 1 minus t power 16 by 1 minus t whole power 4. So I want the coefficient of t power 40 in this expansion. So this is 1 minus t power 16 whole power 4 into 1 minus t whole power minus 4. 1 minus t whole power minus 4. So this I can write it as 1 minus 4 t power 16 plus 4c2 is 6 t power 32 minus 4 t power 48 plus t power 64 into This I am going to expand using our formula. So this is 1 plus this is k is equal to 4. What will be the coefficient of n here? N plus k minus 1 c, k minus 1. So this is n plus 3 c3. So this is 1 plus 3c3 into t plus 2 plus 3c3 into t square and so on. So when will the coefficient of 40 come? When I multiply 1 by the t power 40 term. Correct? That's one way it will come. So what will be that one? That is t power 40 is, this is 43 c3 minus, whenever I have this term multiplied by, I have 16 here. So I have a 24-degree term. That also will come, yes, 40. So this is minus 4 into, what's the coefficient of 24 here? So this is 24 plus 3 c3. Then this 32. Then I have to multiply by t power 8 here. So plus 6 into the 8, isn't it? 8 plus 3c3. So I have 43c3 minus 4 into 27c3 plus 6 into 11c3. So this will be the coefficient, this will be the term, this will be the number of solutions to this equation. Okay? This will be the number of things to this equation. Of course, we can, I can see what this guy is, not that difficult, but the answer is, no, the final answer is not, but we are interested in how we arrived at this expression. That's what this one. Okay, right. So now let us observe an important difference between this one and then what we have already seen before. Now here, what we wanted was the number of solutions to the equation x1 plus x2 plus x3 plus x4 equal to 40, in which 0 less than or equal to xi less than or equal to 15. Correct? So we need to go through all this method and so on. Okay. However, suppose you are asked, suppose I have the same question, x1 plus x2 plus x3 plus x4 is equal to 40, such that each xi is greater than or equal to 5. Each xi is greater than or equal to 5. Okay. Suppose if I am asking that question, this is easy because I can define this yi is xi minus 5. Then what will happen now? My y1 plus y2 plus y3 plus y4 will be equal to x1 plus x2 plus x3 plus x4 minus 20, which is equal to 20. So what I want is, I want a number of solutions to y1 plus y2 plus y3, 4 equal to 20. What is the condition on this one for me? So y xi is greater than or equal to 5, it is greater than or equal to 0. No other conditions. So y is greater than or equal to 0. So this we already know by stars and bars is 20 plus 3 c3. So whenever I have condition like which is greater than or equal to something, it's a very simple stars and bars. Simple stars and bars. If it is less than or equal to something, then what happens is that then I have to look at either using this generating functions like this or pi. So pi will come only when I have a less than or equal to condition. Whenever I have all the conditions are greater than or equal to that, then I don't have a problem. It will be just a simple application of stars and bars. Right? Okay. Right. So the last class I also told that we can derive some binomial identities using this method. So let me show you a couple of examples for that. Right. Now, let's look at this for instance. Hope you remember this this identity. It is called the hockey stick identity. This is hockey stick identity. And we proved it using a counting argument before. So now I am going to use this generating function method. Okay. Let's look at this right hand side first. Right hand side is MCM plus M plus 1 CM and so on up to M plus NCM. Now this MCM comes as coefficient of t power m in 1 plus t whole power m. Because when I have binomial theorem, what will happen? If I expand it, it will get, meaning it will get MC0 plus MC1 into t plus MC2 into t. So this will be what? MC0 plus MC1 into t, MC2 into t square, and so on up to MCM into t power m. So this MCM comes as the coefficient of t power m in this expansion. Similarly, what will be this one? This will come as a coefficient of t power m in 1 plus t whole power m plus 1. Because m plus 1, then expand, what will I get? I will get m plus 1 cm into t power m. The next term is m plus 1 cm plus 1 t power m plus 1. So this is the term which is t power m. So that means this is the coefficient of t power m in 1 plus t whole power m plus 1. Similarly, the last term is the coefficient of 1 plus t whole power m plus n. So what happens now? I have, this is actually the coefficient of t power m in this expansion, which is 1 plus t whole power m plus 1 plus t whole power m plus 1 and so on up to 1 plus t whole power m plus n. Okay. So if I call this as, let us say, some x, we call this as x, then this is my x power m, this is my x power m plus 1 up to x power m plus n. So plus. So this I can take x power m out, it will be 1 plus x square up to x power n. Yes, Diana.
Wait, why is the last term m plus n? Because it says that the largest term is n choose m. It's not m plus n choose m. So I'm kind of confused.
No, what is it again? M plus. So if in the last term is what? Last term is m plus n cm, correct? So
but in the question, doesn't it say n choose m? Not m plus n choose m?
Oh, I see. Oh, that's what I got, isn't it? No, but yeah, you are right. So I didn't. Okay. Let's change that. Don't worry. Okay, I have n choose m. That means I have, this is the last one is n choose m. Yeah, thank you. So this will be m plus 1 up to, this will be n choose m. Correct? That is n choose m. Of course, we know that m is less than n. So I keep on going up to this one. Okay, now, right. So I get this. That's correct. Okay, right. I can do this. I can do this. So what will happen is that this is my up to n. This is also up to n. So I get up to n. So what will happen here is that I have my x power m. If I take out, it will be x power n minus m. That's what it will become, isn't it? So I can take x power m is common on all these terms. I get x power m into 1 plus x square x power n minus m. So this is equal to x power m into, this is geometric series again. So what will be that one? Okay, 1 second. Just hold on.
So this is a geometric sequence, right? 1 plus
Yeah. That 1 second. I'm just sending a message and come back. Yeah. Okay. Yeah. This is a geometric series. 1 plus x square, etc. So this will be what? This will be 1 minus, or I can write it in this form. This x power n minus m plus 1 minus 1 by x minus 1. Correct?
Yeah.
Because when I have 1 plus up to x power r, I get x power r plus 1 minus 1 by x minus 1. Now, what was my x here? X was 1 plus t. Let us put that back here. So it will be 1 plus t whole power m into 1 plus t whole power n minus m plus 1 minus 1 by 1 plus t minus 1. So what I want the coefficient of x t power m in this. This will be 1 plus t whole power m into 1 plus t whole power n minus m plus 1 minus 1 by t. So let us bring this back again. So this will be 1 plus t whole power m into n minus m plus 1 is n plus 1 minus 1 plus t whole power m divided by t. So what I want the coefficient of t power m in this one. So since I have a t below, so I want the coefficient of t power m plus 1 in the numerator. So if I have a coefficient of t power m plus 1 in the numerator, you can cancel out one t and get the coefficient of t power m here. So t power n plus 1 in, so what I want here, coefficient of t power n plus 1 in 1 plus t whole power n plus 1 minus 1 plus t whole power n. Now this term will not have a m plus 1 term at all, t power, because the largest power will be t power m here. So this will, so only this one will have. So this one is basically it is n plus 1. So what's the coefficient of t power n plus m plus 1 here? It will be n plus 1 c m plus 1. So we have got the left hand side here. So we started with the right hand side and observed it's the coefficient of t power m in this expansion. And that expansion we simplified like that. And then computed the coefficient of t power m plus t power m on the right hand side and showed that it is equal to t power m. It's equal to this one. So this is a generic method which can be used to show this kind of identities. Okay. Let me show you one more example. The same thing. Let's look at this for instance. So I have 1 into NCM plus 2 into n minus 1 CM plus R into n minus R plus CM and n minus m plus 1 into MCM. Because see here, how did I get this one? So whenever I get, note that if I add these two, I will get n plus 1. I get n plus 1. I get n plus 1. So I should get n plus 1 here also. Therefore, I already have a m. So only when I add n minus m plus 1 plus m, I will get n plus 1. So this coefficient will be n minus m plus 1. Correct? Yeah. What is m is equal to n? So when m is equal to n, the left hand side becomes mcm, which is 1. The right hand side also, the right hand side becomes mcm because there's nothing more than that. It just starts with mcm and ends there. The right hand side becomes m plus 1 c m plus 1, which again is 1. So there also it is satisfied. So no issues. Okay. Right. So let's look at, let us look at this for instance. So now the same method will work. So what we want to do is that, so I have the right hand side is the coefficient of, this is the coefficient of t power m in 1 plus t whole power n. This is the coefficient of t power m in 1 plus t whole power n minus 1 into 2. And similarly, I have this. So I want the right hand side will be the coefficient of t power m in this expansion. In this expansion. So what is my expansion? S is equal to 1 into 1 plus t whole power n, 2 into 1 plus t whole power n minus 1, and so on up to n minus m plus 1 into 1 plus t whole power m. Okay, so let's put, for instance, 1 plus t as some x. So this is 1 into x power n plus 2 into x power n minus 1, etc. up to n minus m plus 1 into x power m. So in the last case, we had a very simple way to simplify this. Here it is, this is what is called the arithmetico-geometric progression. I don't know how many of you have encountered this. So this is a combination of two progressions. See, the coefficients are all arithmetic progressions. The powers are all geometric progressions. So how do I sum up this? I have an arithmetico-geometric progression. Okay. So what I will do, this is my S. So I will once multiply by x on both sides. I will get 1 into x power n plus 1 plus 2 into x power n plus 3 into x power n minus 1 and so on up to n minus m plus 1 into x power m plus 1.
Not yet.
Hello? So please mute, please, if you are doing something else. My S is x power n plus 2 into x power n minus 1 plus 3 into x power n minus 2 and so on. This is my n plus. No, this is what. Yeah. So this sx n plus 1. Okay. Now if I subtract that, what will I get? S minus s. Sorry, sx minus s. Sx minus x. This will be same as this term will remain. That will be x power n plus 1 term will remain. I have a 2x power n and I have x power n. If I subtract this, I will get x power n. I have a 3x power n minus 1 and the 2x power n minus 1. So if I subtract, I will get x power n minus 1 and so on. I have a n minus 1 whole power x power n plus 1. The previous term would have been n minus m whole power x power m. And that will be the, sorry, n minus m plus 1. S was what? N minus m into x power m. No. What am I doing? So what is the previous term? This is n minus m into x power m. That's what I will get. And x power n minus 2 is 4x power n minus 2. I'm saying x power m plus 1 term will be x power. No, 1 second. Let me be careful here. 1 second. Yeah. So what do I get here? So let me carefully write this guy down. So I have. So we have a problem. 1 minute. So what I have written here. So it is x power m. Correct? That's correct. So what I have here is. So s is 1 into x power n plus 2 into x power n minus 1 up to n minus 1 x power n plus 1. So I am multiplying by x. What will I get? 1 into x power n plus 1 plus 2 into x power n plus 3 into x power n minus 1 and so on up to n minus m plus 1 whole power x power m plus 1. Correct? So here I have 3x power n minus 2. So if I multiply by x, I will get 3x power n minus 1. My x is 1 into x power n plus 2 into x power n minus 1 and so on. And the previous one, the last one, x power m is there. X power m was that. X power m is n minus m plus 1 into x power m. And this term is not there. So this term is here. So the previous term was what that? This will be n minus m. Correct? N minus m. 1, 2, 3. So n minus m. This should be what? 3, right? So it is increasing. So it will be n minus m into x power m. N minus m into x power m. So if I multiply by, this will be s minus sx is like this. And yeah, so this term, so this is the last one is n minus m plus 1 into x power m. The previous term was n minus m into x power m minus x power m. What I'm saying. 1 second. There is one mistake. So if my x is what? X is 1 into x power n plus 2 into x power n minus 1 and so on up to x power m. So this is n minus m plus 1 into x power m. So what is the previous term would have been? The previous term would have been, so 1, this is increasing. So it should be n minus m into x power m minus x power m plus 1. You note that the powers are decreasing. So the previous term is n plus 1 and this is my m. Note that the coefficients are increasing. So this term is n minus m plus 1. So this should be n minus m. So now we are in shape. Now if I subtract, like what will I get? I will get this term will remain x power n plus 1. So x power n minus 1 and so on. And this one will give me x power m plus 1. And minus of this will remain n minus m plus 1 into x power n. This is my. So this one, what will I get is that, so I will just simplify this way. This will be x power m plus 1 into 1 plus x etc. up to x power n minus m. Up to this will be there. Minus n minus m plus 1 into x power m. This is my s into x minus 1. So my s will be this quantity by x minus 1. So that's what we want. Now we are almost there. Right. Okay. So I have written like this one, replacing. So I get this by t, n minus m plus 1. So this one up to this I already have got. So this is my s into, so this is my sx minus x. So what will I get is just this. This is what I get. Now, what I want here is that I want the coefficient of t power m in this one. Coefficient of t power m in this one. So here I want the coefficient of t power means I want the coefficient of t power m plus 2 in this one. And here I want the coefficient of t power m plus 1. So this will not have a coefficient of t power m plus 1 because the highest term is m. Only here it will be there. So I want the coefficient of t power m plus 2 in the numerator. And again, this will not have a m plus 2 term. So it will be only this one. So n plus 2 is m plus 2. So that's what we have. So this is slightly involved, but the thing is the basic idea is simple. So we write it as a coefficient and then summing up. See, for instance, here, if I have a sum like this, a plus d into r plus a plus 2d into r square, etc. up to a plus nd into r power n. So you must know how to sum up this kind of meaning combined progression, that is arithmetic or geometric series. And again, the same method will work. You just multiply with the common difference. This will be AD plus this will be A plus D into R square and so on up to A plus ND into R power N plus 1 and then subtract. So these terms will automatically cancel out. That is AD, so A plus D into R square. So this is A plus D. So if I subtract a plus 2d into r square, a plus d into r square, I can cancel out. So similarly, it will be a into 1 minus d and so on. So you can just easily sum up this one. So that's the usual trick which is used. AD and no, you just multiply by r, AR square and AR power n plus 1. So R. So it means if I just subtract that, I will get A will remain. So DR will remain. ARs go away, and then again DR square will remain and so on. So that's what the trick is. Okay. Right. And let's look one more problem. Let's find the number of solutions in non-negative integers to the equation x1 plus x2 plus x3 plus 2x3 is equal to n. So each x is non-negative. That means I can write it this way. I want the coefficient of t power n in 1 plus t square, etc. into 1 plus t square, etc. into 1 plus t square plus t power 4 plus t power 6, etc. Correct? Because every term is of the form even number. So I have 1 plus t square plus t power 4. So if I take t power x1 here and then t power x2 here and t power 2x3 here, whenever I have x1 plus x2 plus 2x3 is n, I will get a coefficient t power n. Correct? That's what it is. So now this is 1 by 1 minus t. This is 1 by 1 minus t. This is 1 by 1 minus t square. So I want the coefficient of t power n in this. Now I can write it in this form. There is 1 by 1 minus t whole square equal 1 minus t square, right? There are several ways to do this, but we will give you the shortest way. So I have 1 minus t square here, and I have 1 minus t whole square here. So by multiplying and dividing by 1 plus t whole square, let's see what happens. 1 plus t whole square into 1 minus t square, which is same as 1 plus t whole square divided by This is 1 minus t square square into 1 minus t square. So this is 1 plus t whole square by 1 minus t square whole cube. So what I want is 1 plus 2t plus t square, which is this numerator, into 1 minus t square whole power minus 3. So I have to find the coefficient of t power n in this. Okay. Now, suppose my n is even. If n is even means, when will the term t power 2m come? Then n is equal to 2m. And I multiply 1 by the coefficient of t power 2m here. Or when I multiply t square by the coefficient of 2m minus 2. What's the coefficient of t power 2m in this one? So this is like 1 minus t square whole power minus 3. Suppose if I have my 1 minus x whole power minus 3, the coefficient of x power n is n plus 3 minus 1, see 3 minus 1. Right? So here it is n plus 3 minus 1, see 3 minus 1 whole power t power 2n. So the coefficient of t power 2n will be n plus 3 minus 1, see 3 minus 1. That is n plus 2 c2. That means the coefficient of t power 2m is m plus 2 c2. M plus 2 c2. Plus this one multiplied by t power 2m. This is same as t power 2 into m minus 1. So what will the coefficient of t power 2 into m minus 1? It will be m minus 1 plus 3 minus 1, say 3 minus 1, which is same as m minus 1 plus 2 is m plus 1. So m plus 1 c2. This is m plus 1 c2. So this m plus 1 c2 and then m plus 2 c1. So I have m plus 2 c2 plus m plus 1 c1. So this will be the coefficient of when n is equal to 2. And you can easily simplify this to this one. So that's not very important. When it is 2m plus 1, only one term will remain. That is 2 times that into what? 2 times that into t power 2m. 2 times that into 2m. We already saw that t power 2m coefficient is m plus 2 c2. So it is 2 into m plus 2 c2 when it is odd. When it is even, it is this, and when it is odd, it is this one. So that's what. So we can easily solve this kind of problems. Okay. Right. So let's move forward and yeah. That's yeah. Okay. The question is x1 plus x2 plus x3 plus x3 is equal to n, and apply stars and bars. Can be. See, when it is x1 plus x4, when x4 is, see, we have a condition on x3, that is x1 plus x2 plus x3 plus x3 will give me all solutions in which x3 need not be, these two can be different also, isn't it? So this won't work. For instance, I have suppose my n is 10. It will give me 1 plus 1 plus, let us say, 3 plus 5. That also is part of the solution. But that solution we do not want because these two should be equal. So I can't do that. I can't just trick that way. Because these two x3s are the same means I cannot use stars and bars generally. So it's not the case at all. Okay? But we can't do that. Okay. Now, let's look at this problem. So we have 3 people going out for dinner. So they want to agree to split the bill 50 in the following way. So she says that she will contribute a number of dollars, a multiple of 3. And Ria and Leela each will insist on contributing an odd number of dollars. So how many ways can they split the bill? Okay. So that means Ria can give 2x1 plus 1. Leela can give 2x2 plus 1. And then Meera can give 3x3. So I want this plus this is equal to 50. Where each xi is greater or equal to 0. Correct? Xi is greater or equal to 0. So my 2x1 plus 2x2 plus 3x3 must be equal to 48. Yes, Diana.
Can't you write it as 6x3 since Mira has to give an even amount to make it 50? Since Ria and Lila are both contributing odds, so can you write it as 6x3?
Yeah, it has to be 6. We'll come to that. Yeah, that's a good observation. So you're going to make that and then make the problem, solve the problem using that one. Because see, if we have x1 and x2, the x3 has to be even. X3 has to be necessarily even. So that means I should have 6x3 and so on. Anyway, we'll come to that. We will apply that your observation towards the end. Okay. Right. So I have 2x1 plus 2x2 plus 3x3 is 48. So this will be coefficient of 48 in t power 4 etc. into 1 plus t square t power 4 etc. into 1 plus t cubed plus t power 6 etc. So this is 1 by 1 minus t square whole square into 1 by 1 minus t cubed. Correct? So this is same as 1 minus t cubed power minus 1 into 1 minus t square whole power minus 2. Note that all the terms here will have even powers. Here also there should be even powers. So we need to consider only t power 6, t power 12, etc. So I can write this as is the same as coefficient of t power 48 in 1 minus t power 6 whole power minus 1 into 1 minus t square whole power minus 2. Because I don't want this t cube term. Then what will come here? Will be 1 plus t cube plus t power 6 plus t power 9, etc. I can ignore all these odd powers. So what will remain? 1 plus t power 6 plus t power 12, etc. Which is same as 1 by 1 minus t power 6. So I have written it that way. So here we have that. Correct? So I need that. Okay. Now, so what I have here, so I want 1 minus t power 6. So just as in the previous problem, I want to convert this into 1 power t power 6 so that I can easily apply the theorem. So if I have this 1 minus t square whole square I have. So if I have 1 minus t square into 1 plus t square, sorry, 1 plus t square plus t power 4, this will become 1 minus t power 6. You know this formula, a minus b into a square plus ab plus b square will be equal to a cubed minus b cubed. So I have 1 minus t square, a minus b is 1 plus a square plus b square is t power 4 and then b cubed is, sorry, ab is t square and then a square, b square is t power 4. This is what 1 minus t power 6 is. So if I do that, so since I have square here, I have to multiply with this also. So the coefficient of t power 48 in this, that's what I want. Same method is coefficient of t power 48 in t power 4 whole square into 1 minus t power 6 whole power minus 3. 1 minus t power whole power minus 3. I'm going to expand this. Of course, most of you will know how to expand a plus b plus c whole square. This is same as a square plus b square plus c square plus 2ab plus 2bc plus 2ca. That's what I have written here. Correct? A square plus b square. So you can expand it, I will get that. So I want the total is 48. That means here everything is in the form 6, 12, 18, 24 and so on. So when will I get? I will get 1 into t power 48. So when will t power 48 come? When n is 8. That means it is 10c2. It is 10c2. Again, next time when it will come, so this is t square into I have t power 46 will not come here. T power 4 means 44 will not come here. T power 6 means 42 will come when n is equal to 7. T power 47 term will multiply it by t power 42 term multiplied by t power 6 term will give me 48. So I have 2 into t power 42. So t power 42 means what? This is 7. 7 plus 2c2. So I have 8 plus 2c2 plus 2 into 7 plus 2c2. This is 10c2 plus 2 into 9c2. So this will be 11. So I think it's correct. Let me check. 10 into 9 by 1 into 2, which is 45. And 2 times 9 into 8 by 1 into 2, which is 36, 72. So 72 plus 45, 170. So that's okay. So that's what we used. So these kind of problems are not easy in any other method. Okay, so this pi cannot be applied because we are trying to solve this kind of equations. Okay, So even in this case, I have my 2x1 plus 2x2 plus 6x3 is equal to 48. Even if I do that, I have my x1 plus x2 plus 3x3 must be equal to 24. So even this one, we have a, we may not be able to use pi directly, and not many other methods will work. So this is the only method which will work for this kind of, particularly when I have an equation in which I have coefficients. Okay, there is there's one more way. No, but that won't work all the time. Okay, don't, sorry about it. Yeah. Let's use this problem. It's slightly a different type of problem. Let's think about this first and see what kind of ideas we will try to use. I have a sequence x1, x2, xn. We will call that as a binary sequence if each xi is either 0 or 1. For instance, 1, 1, 0, 0, or even 0, 0, 0, 0, or 1, 1, 1, 1, 1, like that. So I have a sequence of digits. All of them are either 0 or 1. We'll call that a binary sequence. I want to find the number of binary sequences of length 20. There are 20 symbols here, which contain exactly 3 occurrences of 0, 1. Exactly 3 occurrences of 0, 1. So for instance, this sequence 0, 1, 0, 1, this contains 2 occurrences of 0, 1. If you look at 0, 1, 1, 1, 0, this contains only 1 occurrence. 1, 1, 1, 1, 1, 0 occurrence. Or 0, 1, 0, 1, 0, 1. Then I have 6. If I just add 14 zeros, this is one such sequence whose length is 20, but exactly having 3 occurrences of 0, 1. Or like the 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. How many are there? 2 plus 5, 7, 8, 13, and 1, 14, and 6 zeros. Is another sequence which has length 20 and having exactly 3 occurrences of 0. Exactly 3 occurrences of 0, 1. Correct? And if you want that, so I have, suppose I want the length of number of sequences in which length 4 that contain exactly 1 occurrence. I have this one, this one, this one, this one. I have only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are. There are only 10 such sequences. Okay. But I want 20, length 20, but it should have exactly 3 occurrences of 0, 1. Okay. Exactly 3 occurrences of 0. Of course, doing it by brute force will be difficult. So we want to do something else. Okay. Right. Can you, suppose I length 4, can you write down all the sequences that have no 0 1s? Can you find out all the sequences that have no 0 1s? Should not contain 0, 1 at all. Okay, all the sequences which have no 0 1s. Of course, this is one. This is another. This is another. This is another. This is another. Anything else?
I think there are only those 5 because all the ones have to be before the zeros. Otherwise, there's a 1 after a 0.
So these are the only 5. I have length 4, which do not contain 0, 1 is just that one. So, more generally, if I have k, length is k, and I want no occurrence of 0, 1s at all, there should be k plus 1 of them, because all the 1s must appear before the 0. That means here there is no 1, here there is 1, 1, here there is 2, 1, here there is 3, 1, and so on up to all of them. There are k plus 1 binary sequences of length k that have no occurrence of 0, 1. No occurrence of 0, 1. Correct? That have no occurrence of 0. Isn't it? Now, our idea is this. I want m occurrences exactly. Let us say. Let us say I want 3 occurrences. That's what we want. So I have 3 occurrences. I will put 0, 1 here, 0, 1 here, and 0, 1 here. Totally, I want 20. Correct? The length has to be 20. So I have already accounted for 6 of them. So I have to add 14 of the symbols. Where can I add the 14 of the symbols? I could add here, or here, or here, or here. So what are the things I can add here? Whatever I add here, it should not have any 0, 1 at all. Because if at all it has a 0, 1, then that would add to this number 301. So I don't want that. So I can add 4 sequences. I can add 4 sequences that do not contain any 0, 1s at all. And suppose this length here is x1, and this length here is x2, and this length here is x3, this length is x4. So what should contain now? I should have my x1 plus x2 plus x3 plus x4 must be equal to 14. What are all the possibilities for this x1? What are the possibilities for this x1? So it's a length of sequence is x1. So how many possible ways of filling this x1 symbols is x1? They should not contain what? That should not contain any 0, 1. So I have x1 plus 1 such sequences I can fill here. Correct? x1 plus 1 sequence I can fill here. Similarly, I can fill here x2 plus 1 sequences. This I can fill in x3 plus 1 sequences. This I can fill in x4 plus 1 sequences. Correct? So the total number of sequences I can get once I do that is x1 plus 1 to x2 plus 1 to x3 plus 1 to x4 plus 1. What's the condition on x1, x2, x3, x4? So I have to find the number of solutions. Whatever the solution, I can have this one. So this will be the sum of all these things such that my x1 plus x2 plus x3 plus x4 equal to 14. Okay. So for any such solution, I have these many sequences. So I look at all the solutions here. All the solutions. So what are the solutions possible? X is greater than or equal to 0. How many solutions are there? I have my 14 plus 3C3. I have 17 C3 solutions. For each solution, I have to find this product and sum all of them up. So if I do that, then I will get the number of solutions. Correct? It looks like a difficult problem, isn't it? So I have my x1 plus 1 and x2 plus 1 and x3 plus 1 and x4 plus 1. I have to do that. When x1 plus x2 plus x3 plus 4 is 14, I have 17 C3 solutions. So one solution, let us say, is 2 plus 3 plus 7 plus 2. So for this solution, how many sequences I will have? I will have 3 into 4 into 8 into 3. 9, 36 into 8. So I will have for this one solution, I will have how many things I can get? I can get 288 sequences for just one solution. So how many solutions are there? 17 C3 solutions are there. So how do you sum up all these guys? Okay. Okay. Now let's make a smart observation. So this is what we want. So what we want is, we saw sometime back 1 plus 2t plus 3t square plus 4t cube. What is this one? This came in one of the expansions. So this is same as 1 minus t whole power minus 2. 1 minus t whole power minus 2. Okay. So if I write this 1 plus 2t plus 3t square, etc. up to whatever. Okay. Whole power 4. Whole power 4. And if I find the coefficient of t power 14 in this, what will I get? When will coefficient of t power 14 come? So the coefficient of t power 14 will come whenever I have a t power x1 here and a t power x2 in the second factor, t power x in the third factor, t power x4 in the third factor. So this product has to be t power 14. Therefore, my x1 plus x2 plus x3 plus x4 must be equal to 14. In that case, what will be the coefficient of this chap? This chap will be just x1 plus 1 because t square coefficient is 3. T cubed is 4. This coefficient will be x2 plus 1. And this is x3 plus 1. This is x4 plus 1. So the coefficient of, for any such solution, the term which comes in this one is just this one, that is x1 plus 1 into x2 plus 1 into x3 plus 1 into x4 plus 1 into t power 14. So the sum of all these guys will be what I wanted. So it is same as finding coefficient of t power 14 in this expansion. So what is that now? That t power 14 in this expansion. I already know that thing is t power minus 2. What I want is 1 minus t whole power minus 2 whole power 4, which is 1 minus t whole power minus 8. In this, what I want the coefficient of t power 14. Coefficient of t power 14. Here my k is 8. My 14 is, n is 14. So this t, it is 14 plus 8 minus 1, see 8 minus 1. 14, this is 21, see 7. So this will be the sum of all these guys. Correct? So now see, we didn't do any computation at all. We just made two observations. One observation is that 1 plus 2t plus 3, this is actually equal to 1 minus t equal to minus 2. And whenever I expand minus 4, I get the sum, the coefficient of t power n in all these things will be same as, so here this coefficient occurs in x1 plus 1, is x2 plus 1, so on. So whenever I have my x1 plus x2 plus x3 plus x4 is equal to sum n, I get the sum of all these things as that x1 plus x4 equal to n. So even though, so this is x1 plus x, so this automatically sums up, the coefficient automatically sums up these things. So I have 17 C3 solutions. But when I sum up all these things, what I get is 21 C, what is the things I got? 21n plus 8 C7 or 21 C7. So that's what we got. So this will be the number of such sequences of length 7 and so length 20 having exactly 3 zeros, correct? Yes. Okay. So the form of the answer which is this 21 C7 is very compact, right? And also it's pretty simple one. So is there another method which will not do any of these things but still arrive at this answer in a very simple way? Okay, let's look at that. Okay, let's look at any sequence. Okay, let me check that, observe that one. Yeah. Yes, Arnika.
Sir, could you please explain like the last part of this solution? I didn't quite get that.
Yeah. Yes. Okay, let's go back here again up to this. Okay. Let me explain the full solution so that we can appreciate it better. Okay. Right. So we first observed that there are k plus 1 sequences of length k which do not contain any 0 1. Correct? That's obvious because every one has to become before the zeros. So it has to be the only possibilities. These are the k plus 1 possibilities. Now I want to put 3 0 1s. So I put those 3 0 1s. Now these things account for only 6 length. So I want 14 more. At 14 more, I will put some x1 symbols here, x2 symbols here, x3 symbols here, and x4 symbols here. So then such that my x1 plus x2 plus x3 plus x4 is 14. But what should this x1 symbol must be? This should never contain 0. Correct? This should never contain 0, 1. This also should not contain 0, 1. This should contain 0, 1. This also should not contain 0, 1. So this x1, if it not contains 0, 1, if its length is x1, how many possibilities are there for such a sequence, that is such a sequence of length x1, such that not containing any 0, 1. For this I have x1 plus 1 possibilities. Similarly, for this one I have x2 plus 1 possibility. So note that this and this multiplication principle tells me this I can fill in x1 plus 1 ways, this I can fill in x2 plus 1 ways. So the total is I can fill in x1 plus x2 plus x1 plus 1 and x2 plus 1 ways. This x3, again that will have x3 plus 1 and x4 plus 1. So the number of sequences will be, for any such solution x1 plus x2 plus x3 plus x4 is equal to 14. I have to sum up all these guys. Note that all these sequences will be distinct also, because if x1 and x2 vary, the corresponding sequence also varies. This is what I want to find. So where my x1 plus x2 plus x3 plus x4 must be equal to 14. So I want to evaluate this sum. So this sum, the first observation is that, suppose if I expand 1 minus t whole power minus 2, what's the coefficient of x power t power n in this one? So coefficient of x t power n is n plus 2 minus 1c, 2 minus 1, which is same as n plus 1c1, which is same as n plus 1. So here the coefficient is, this is same as 1 plus 2t plus 3t square plus 4t cubed and so on. So this x1 plus 1, x2 plus 1, x3 plus 1, x4 plus 1 gives us an idea that I will get, whenever I multiply 1 minus t whole power minus 2 into 1 minus t whole power minus 2 into 1 minus t whole power minus 2 into 1 minus t whole power minus 2. What will be the coefficient of t power n in this one? So coefficient of t power 14 in this one. So I would have got a t power x1 here. I would have got a t power x2 here, t power x3 here, t power x4 here. What's the coefficient of t power x1 here? It is x1 plus 1. This x2 plus 1. The coefficient of x3 is t power x3 is x3 plus 1 and x4 plus 1. So whenever I take the term t power x1 here, t power x2 here, t power x3 here, and t power x4 here. So what will I get? What will be the coefficient of this when x1 plus x2 plus x3 plus x4 is 14? I will get the t power 14 term. What will be that coefficient? Coefficient will be this coefficient x1 plus 1 into x2 plus 1 into x3 plus 1 into x4 plus 1. So what will I get is, this is the form x1 plus 1 into x2 plus 1 into x3 plus 1 into x4 plus 1 into t power 14. So how many such t power 14s will come? As long as I have this product, as long as I have my x1 plus x2 plus x3 plus x4 is equal to 14. Correct? So this is the key step. So once I understand that this sum, the sum which I wanted, is same as coefficient of t power 14 in 1 minus t power minus 2 whole power 4, which is same as 1 minus t whole power minus 8. So my coefficient of t, I want the coefficient of t power 14 in this one. So in my 1 minus t whole power minus k, what's the coefficient of t power n generally? N plus k minus 1 c, k minus 1. Here what is my k? K is 8. So I have 14 plus 8 minus 1 c, 8 minus 1, which is same as 21 c7. So that's what so I wanted the coefficient of t power 14 and it is 21 c7. So we have got it. So okay, Arnika?
Yes, sir. Thank you.
Yeah. Okay, now let's look at one more method of doing this. Okay, without doing any computation, by making a simple observation. Okay. Now let's look at any sequence. Let's say 0. I have 0, 1, 0, 1, 0, 1. Let's say 0, 0 here. Okay. So how many 1 zeros will be there? Suppose I have 3 0 1s. Length is 20. How many 1 zeros will be there? In this case, how many 1 zeros are there? 1 and 2. There are 2 1 zeros. There are 3 0 1s and 2 1 zeros. Anything else is possible? I have 0 1, okay, and 0 1 and 0 1. So this also has 3 0 1s, but how many 1 zeros are there? I have 1, 2, 3. In this case, how many are there? There are only 2. This is 0 1, sorry, 1 0 and a 1 0. So this has only 2. This had 3. Right? This had 3. So anything else is possible? Suppose I add a 1 here. How many 0 1s are there? 1 0 1 2. Only 3 0 1s, but 1 2 3 4 1 zeros are there. Suppose I have 3 0 1s in the sequence. The number of possibilities of 1 zeros is either 2, 3, or 4. Right? It could be like 1 less, or exactly same, or 1 more. Suppose I have 3 0 1s. So the number of 1 zeros will be either 2, or 3, or 4. Either 2 or 4, 3 or 4. Correct? Okay. Right. So what we will do, suppose you take any one sequence like this. So suppose I take any one sequence. Suppose if I take a sequence like 0 1 0 1 0 1. And we add a 1 before and a 0 after. We add a 1 before and a 0 after. Will this change the number of 0 1s? Will this change the number of 0 1s? Because I am not adding, so it will be 1 0 1 0. So it will not change the number of 0 1s, but it will change the number of 1 zeros to exactly 3. Sorry, exactly. No, exactly. How many will be there? Yeah, in this case, I have 1, 2, 3, 4. It will be 4 of them. Correct? So you have to find something like that. So it will be 4 of them here. Correct? It will be 4 of them. So suppose if I have I have to check something like this. Yeah. So I have 4 1 0. So whenever I have 3 0 1s, if I add a 1 and add a 0 at the end, it will add exactly 3. It will have exactly 4 1 zeros. So how many transitions will be there? Transition meaning either 1 to 0 or 0 to 1. So there will be, I have these 4 transitions will be there, and this will be 3. Therefore, there will be total 7 transitions will be there. That means I have a symbol. I started with 20. So I have 22 symbols now, x1, x2, etc. up to x22. I added 1 0 below, and after 0, I have 22 things are there. Here I should have 7 transitions. So suppose suppose I know that the transitions happen either here or here or here, like that. So out of these 21 steps, I have to choose 7 of them. Say that they are the transitions. For instance, here I have, let us take this example for instance. I have my 1, 2, 3, 4, 5, 6, 7, 8. So I have my 8 symbols. 1, 2, 3, 4, 5, 6, 7, and 8 symbols are there. Where all the transitions happen, I have a transition here. I have a transition here. I have a transition here. I have a transition. All of them are transitions. So that means, so if this a transition is 1, it has to be 1 0 here. It has to be 0 1 here and 0 1 here, 0 1 here. So it will be uniquely determining the sequence itself. So once I know where the transitions happen, correct, I can easily find out what the solution. Suppose I have, let us say 1 1 1 0 1 0 1 1 1 1 1 0 1 0. Where are all the transitions happening? At this point. And the next transition happening at this point. This happening at this point. And this happening this point. and this happens this point, and this point, and this point. There are 7 transitions. So once I say that these are the transitions, the first transition has to be 1 to 0 because I added a 1 here. So all the previous ones has to be 1. And next I have to be 0, and then up to the next one it will be 0. So for instance, the transition, suppose I have a same thing. Let us say I have a transition x1, x2, x3, x4, x5, x6, x7, x8. The transitions happen, say x9, x10. I know the transition happen here, 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 and here, here. So what will be the corresponding sequence? This has to be 1, 1, it has to be 0. Here it doesn't happen, so it will be 0. This has to be 1. Here it happens, it has to be 0. Here, so it has to be 0, it has to be 1. So it has to be 1, it has to be 0. And here it has to be 0, here it has to be 1. So here it has to be 0, here it has to be 1, 1 like. So I can always find out what happens when once I know where the transitions actually happen. So it uniquely fixes the sequence also. So I basically it's same as finding I have 22 places. Out of which 21 places I have to choose. 7 places I have to choose for transition. So I have got this. So 21 C7. So it's a simple observation, but it's slightly difficult to understand. So think about that. And if you still have doubts, we will discuss this in a slightly different way in the next class. Okay. Right. So far we have covered almost all counting techniques like addition principle, multiplication principle, and then choose and place, and stars and bars, and pi, and generating functions also. Anything else we missed out? Okay, these are the only ones. Okay. So there is one more which is using recurrence relations that we will study later. Okay, it's not. Now let us summarize what we have done so far. Okay. So for that, let's take a simple problem. We are going to put some objects. Let us say some k of them. Sorry, some n of them into some boxes, some let us say containers. Instead of boxes, let me use the word containers. Some k containers. So these objects, there are 2 possibilities. I have an object here. Let us say there are 2 possibilities. That means either they could be distinct or they could be identical. These containers can be 2 possibilities. Either they could be distinct or identical. So when I place the objects into containers, 2 possibilities can happen. Whether empty containers, empty allowed, or not allowed. There are 2 possibilities here. And the containers can have slightly different thing. For instance, if the container is a bag, let us say, and the objects are distinct, the order within the bags is not important. Order is not important. On the other hand, if it is a shelf, I am arranging books in a shelf, and the books are distinct means, the shelf means if I just, this is the first book, this is the second book, it's a different arrangement than this arrangement. So order could be either important or not important. Okay? So there are these things. Okay. So I have, totally I have 12 possible cases. What are the 12 possible cases? Let me just expand this a bit. Yeah. Okay. So the objects could be distinct, the containers could be distinct, empty containers allowed, or order within matters. This is one of them. For instance, I have n distinct books to k numbered shelves. Because objects, see, containers are also distinct, so the numbered shelves also has to be distinct. Okay. Again, objects could be distinct, containers could be distinct, empty containers allowed, and then again k numbered shelves. So I will leave some of the shelves empty. Now, the same way, if the order is not important, that means I am giving to k students. then I have two more cases, depending on whether every student should get at least one book or not one book. That way. And let's say the objects are distinct, but the containers are identical. That means I have these empty containers are not allowed, and order itself is matter. That means I am putting them into a parcel like this. I have A, B, and I just put this as a parcel like this, or BA as a parcel like this one. Okay, so then the order is important, but I can put it as a parcel. The parcels can be distinct or identical also. Okay? And similarly, I can put the empty containers can be allowed, and for some parcel can be empty and so. Okay. Now, when the order is not important, I'm just putting it in a bag like this. I'm putting the books in a bag like this. So whether I put BA first or AB second, doesn't matter at all. So I have two more cases. And I have, suppose the objects are identical and the containers are distinct, like n copies the same book to k students. So whether I have to give at least one book to some student or not, depending on that, I can have two more cases. The last two cases are this is identical, and of course, see here, the order doesn't matter at all because the books are identical means what does order mean? So this is always no. There can't be yes here because the objects are identical. I can't say that I have an identical book like this, another identical book like this. It will look the same if I just reverse the order also. So that doesn't matter at all. So this is only 4 cases, not 8 cases. So I have identical, distinct, and so on. So similarly here, identical, empty containers are allowed, and then order doesn't matter, obviously. Here, identical, empty containers are allowed or not. Okay, these are identical here, these are identical here. So these are the 12 different cases. These are the 12 different cases. So let's see how many of them we have done already. So let's look at this one. So here I have objects are identical, containers are distinct. So objects are distinct, containers are distinct, empty containers are allowed, order also matters. Order also matters. Right? Now, how will I do that here? So what I'm going to, I have my n, say, distinct books. N distinct books. And I have k differentials. K differentials. So I have to arrange the n distinct books into k differentials. So order matters anyway. Empty is allowed, let us say. Empty is allowed. Empty is allowed. What I will do is that I have my books, let us say A1, A2, etc. up to AN. So I can arrange them in a row in factorial n ways. Factorial n ways, right? Because all the books are distinct, and I arrange them in a row, it will be factorial n ways. Now, what I'm going to do, I've had to transfer these books into k shelves. Some shelves can be empty. Some shelves can be empty. So, what I can do is that I will introduce separators. I will introduce separators. Or what I can do is that I have these books again. I will have k minus 1 separators. I will have k minus 1 separators. So if I arrange these k minus 1 separators in the books in a row, how many ways I can do that? This is n plus k minus 1 c k minus 1. This is the usual Mississippi problem. Why is that? All these things are distinct. These k minus 1s are identical. Okay, so that means I have n plus k minus 1 factorial divided by n plus k minus 1 factorial by k minus 1. No, what I'm saying. Plus k minus 1 factorial by, by k minus 1 factorial. By k minus 1 factorial. So that's what I have, because these k minus 1s are identical. So this n plus k minus 1 factorial will be the same. So I can write this as the number is what? N plus k minus 1 factorial by k minus 1 factorial. Or I can write it as n factorial into n plus k minus 1 c k minus 1. So that's what we have the number of ways. Here that has to be R is given, so k should be k. R both of the same. So I have n factorial into n plus k minus 1 c k. So this is a number of ways of arranging this. So if the things are not allowed means what? Not allowed means I have a1, a2, etc. up to an in factorial n ways, and then I will introduce k minus 1 separators in the in-between n minus 1 factors. So how many ways I can introduce separators? N minus 1 k minus 1 into n factorial. So n factorial ways of arranging the books and then k minus 1 of separating them. So once I put the separators, everybody before the first separator will go to the first shelf. Between 1 and 2 go to the second shelf. Between 2 and 3 will go to the third shelf and so on. This basically stars and bars. The only thing is with the additional condition that these things itself can be arranged in a different way. Okay, usually stars and bars we have identical ones and introduce the plus signs. These itself need not be identical. So I have these two things. Here I have the objects are distinct, containers are distinct, empty is allowed, and then order doesn't matter. So here I have, suppose I have k objects. I have k objects, sorry, k containers, and I have n objects. So I take the first object, they are distinct, right? You can go to any one of the containers. So how many ways it could go to? It would be placed in k ways. Second object, again it could be placed in k ways. Third object, k ways, and k. So it will be n of them. So by multiplication principle, this is k power n. This is k power n ways. Okay. So this is k power n. So let's stop here because the next one is we're going to discuss it straightly. So that means I have read it for 3 of them. Okay. So once we complete all of these 12, then probably, okay, basically we know almost all the counting techniques, all the basic counting techniques, which can be used in any counting problem, meaning any in the sense that most of the counting problems to arrive at the answer, because most of the IOQM problems will be towards this, meaning for instance, counting certain things, number of ways and all those things. So since we already know all the techniques now, so we could choose the correct technique whenever I have when to use pi, and then when to use generating functions, when to use stars and bars, all those things will definitely know once I discuss all these 12 of these cases. Okay, right. So let's stop here and then continue in the next class. Thank you very much, and then good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.